why are all electrons identical? Couldn't you imagine a universe that was just created with 18 billion electrons, and each one had its own serial number? That's not how it works. The way we understand that mathematically now is to say particles are really just excitations of a field. And there are many fields out there. And when I say there are 1 million electrons, what I mean is the energy stored in that field is 1 million units above absolute zero. And it's in that sense that the particles are truly indistinguishable. This thing about half-integral spin, though, when we learn quantum mechanics, one of the first things we learn is that angular momentum is quantized in units of Planck's constant. It can be 10 to the minus 34 joule seconds, or it can be any multiple of that. And then it turns out that the first particle we were worrying about, the electron, violates that so-called rule, and it has half a unit of angular momentum intrinsically. And you just need to accept that. And there's a real mystery about particles that behave that way. I think the way to sum it up is that normal objects, if you rotate them 360 degrees, look exactly the same as before you rotated them. There's a sense in which particles like electrons look like they've undergone a funny flip after you rotate them 360 degrees. And you need to rotate them 720 degrees to make them actually look the same as how they started. And it's that rotation that mathematically we call half-integer spin. It's that rotation that means if you have two electrons and you exchange them, you're doing something that's a little bit different from exchanging two photons or other particles. But like much of physics, it's something where we have the mathematical law and we don't really know to this day what underlies it.
When I'm deep in research, reading papers on, say, the philosophy of mind or quantum gravity, it may seem sterile, but I still don't want my ISP logging every single page that I visit. ExpressVPN prevents exactly that. Your internet service provider, your ISP, can see, they can log, and they can, in the US, legally sell a record of everything you do online. ExpressVPN encrypts all your traffic and reroutes it through secure servers so your browsing history stays entirely yours. I travel for interviews and conferences constantly, and connecting to hotel airport Wi-Fi without protection is something I'd often kick myself for afterward. ExpressVPN's encryption makes those public networks safe. It can be used to totally unlock geo-restricted lectures and content by changing online location to any of 105 countries. There's no compromise on speed either. It's consistently among the fastest VPNs out there. The fragility of hunting for workarounds just vanishes. Find out how you can get up to 4 extra months by clicking the link in the description box below, expressvpn.com/theoriesoferythingyt. That's expressvpn.com/theoriesoferythingyt. What's the largest open problem in quantum information?
The largest open problem in quantum information. I mean, quantum information means different things to different people these days. To me, what's most exciting about quantum information is not that we may one day get better computers. That'll be really cool if it happens. But to come back to my story about my father, I'm a physicist because I care about understanding what we've learned about the universe. And if we can make that useful along the way, that's really great. And if we can point the way and then hand it over to our friends in engineering or our friends in industry, so much the better. Right now, you ask most people what's the biggest problem in quantum information, they'll tell you about the biggest problems towards building quantum computers. And I want to say that's not quite the same thing. So the field still has this foundational side. By discovering the power of quantum information, I think we've discovered new things about how to think about the universe. And we've also discovered paths towards making better sensors and better computers and so forth. The practical problems are twofold. Actually building a large-scale, reliable, fault-tolerant quantum computer. There are a lot of paths that have made amazing progress towards this goal, but actually achieving that fault tolerance while you scale it up remains a huge challenge. And there are promising ways to do it. We don't know how hard each of them will be, which ones will work. And there's a fundamental question. Is there a law of physics we don't know about yet that will make it impossible? We'll come back to that in a second. The other practical question, I would say, is if we had a large-scale good quantum computer, which problems would it be useful for? We don't know the answer to that yet either. We have a handful of problems, and people are working hard to come up with others. And people are making a lot of money claiming to have the answers to others where honestly, they have no evidence whatsoever that there's any quantum advantage. So on the practical scale, those are the two big issues. Make the thing work and figure out if it's good for anything, and if so, what? We know it's good for some things. In particular, we know that it's good for simulating other quantum systems. And I should stress to people outside the physics world, that sounds a bit like a cheap way out, saying, I've developed a device and you're not going to be able to use it for anything interesting, but I can use it to study other devices like it. Feels like cheating, isn't it? Except the whole world is devices like it. You and I are devices like it. All of the antigens in our body are quantum machines. And when we design things we care about, whether those are novel materials that have useful properties, whether those are drugs, whether those are materials for carbon capture, whether they're classical computers, whether they're the kinds of measurement devices that allow us to test, the state of concrete in a bridge, or what our brains are doing when we have some disorder, or anything else, all of that comes down to calculating how some quantum system is going to behave. And we've gotten really good at doing that with classical computers, but there's a limit where it's just way, way beyond us. If we can devise quantum computers that let us solve quantum mechanics problems, that is the fundamental problem we need to solve to do physics, chemistry, engineering, and so forth. So that will be of huge societal impact, even if that's the only useful thing a quantum computer ever does. But even some of those problems, it's unclear. People like to say the first application is going to be quantum chemistry, allowing us to come up with new anode materials for batteries and new drugs. To my knowledge, we have no definitive evidence that that's even possible. We're still trying to figure that out. So there's a lot to be done on that side. On the fundamental side, quantum mechanics, like any other physical theory, is a theory that has worked so far. It seems a little early to have the hubris to think that we're done. Every other time we've thought we were done, we discovered that was a pretty good approximation. But actually, it was an approximation to this more complete theory. So I think we should hope that there's more to discover out there. Maybe there isn't. Maybe this is as close as we get to the final theory, right? I don't know. But quantum mechanics is so good at predicting all of the things that it's predicted, you can't just go and do some other random quantum experiment and say, oh, look, it got it right again. Let me publish more evidence that quantum mechanics is right. You have to be judicious in your choice of where might we expect it to break down, when and if it does. And Bell's inequalities, to me, were the big example of that. Quantum mechanics made a prediction so strange that sane people who cared about the interpretation were saying in the 1960s, I need to check whether quantum mechanics is true as far as it takes to reach this outlandish conclusion, or whether that's where we'll see the breakdown. People like John Clauser were surprised. He expected to show quantum mechanics was wrong, but he's a good scientist. He gave in to his experimental data and said, no, I was wrong. Quantum mechanics still seems to be correct. There are people out there now who say the new frontier is complexity. A lot of people might have said the size of a system. We learn incorrectly that quantum mechanics is the theory of the microscopic world. Well, no, there's no way to draw that boundary cleanly. Even the founders of quantum mechanics didn't know how to draw it, but they didn't need to. They had dozens of orders of magnitude between the atomic scale and their world, and they just assumed that the right description of the macroscopic world was kind of classical, and you had to just understand that there was some transition. But we keep pushing it and trying to look for quantum effects with larger and larger systems. Since the world seems classical to us, the standard common intuition is that the real world is classical, and somewhere along the line, quantum mechanics is going to break down It doesn't describe big, massive systems. That's the view that, for instance, Roger Penrose likes to take. And it's very well motivated because we know that quantum mechanics and our best theory of gravity, general relativity, are not consistent the way we're used to writing them down. Something has to give. So many general relativists over the decades believed quantum mechanics would be shown to be wrong. That was the popular view among relativists when I was a grad student in the 1990s. By now, I'd say it's really flipped. Most of them come from a quantum mechanics background and tend to think that we have to approach the world quantum mechanically and modify gravity to accept that. We don't know what the right answer is, but the kind of Penrose vision is that once objects get large enough that gravity is important, we know the current theory is incomplete, and therefore something else will happen that maybe gives us our classical seeming world. There's a contrary viewpoint that people like David Deutsch, equally brilliant, I would say, follow, and people like Lev Weidman, whom we mentioned before, which is the many worlds viewpoint or relative state interpretation, as its founder, Hugh Everett, described it. At its pared down, most simple level, what this really says is nothing about multiple universes. It says the Schrödinger equation is good enough. That's the law of physics that we've tested. This idea that there are specific instants at which the Schrödinger equation breaks down and a coin flip occurs and we get one thing or another, we don't need that hypothesis. The Schrödinger equation could describe everything. Everything except the fact that you and I think we're having one discrete, well-defined experience now. And that's where I usually take the cheap shot and say, the mystery then is not about the physics. The mystery is about consciousness. The thing we don't understand is not the outcome of any experiment we've ever done in a lab or, any observation we make about the universe, but the fact that our experience doesn't seem consistent with uncertainty. It seems to involve a definite state. In fact, if you think carefully enough about this so-called many worlds theory, you can understand that as well. You can resolve those paradoxes. So it could be that we're somehow experiencing one version of this big quantum superposition, and we don't need that breakdown at all. That's a possibility. But nowadays, thanks to quantum information, many people have taken a different tack. And they've said, maybe the large-scale world does become classical, not because things are so heavy that gravity is important, but because they become complex. And the argument I first heard made by Charlie Rakoff, who's a computer scientist here, came down to asking, how much information can it take to describe a system or to describe the universe? Quantum mechanics says that as you make systems larger and larger, I go from 1 electron to 10 electrons to 20, 30, 100 electrons. The amount of information it would take to completely describe that system grows exponentially. And to Charlie, that was just unpalatable at a metaphysical level. He spent his life thinking about discrete information as a computer scientist. And he says, I can't believe that there exists an exponentially large amount of information. Therefore, I think this theory must be wrong. That's not evidence. That's, again, a quasi-religious feeling. But it's reasonable to say that's the frontier in which quantum mechanics has not been probed. Can we build a 1,000,000 qubit quantum computer and actually have it last in superposition and produce some useful output? It's experimentally really, really challenging, but fundamentally there's no experimental law that says you couldn't imagine doing a good enough job to get there. Wouldn't it be interesting if no matter how hard we tried, it turns out you can't do it. Once you build a system beyond a certain complexity, quantum mechanics breaks down. Maybe that's connected to gravity. Maybe it's connected to consciousness. Maybe it's its own fact. We have no idea. Wildly speculative, right? There's no evidence to say this should happen, but it's one of the few frontiers that have not yet been probed. And one that even though it's incredibly expensive to get there, we now have good motivation, good practical, social, economic motivation to pursue. So that's one of the side effects of the race to a quantum computer. We'll start seeing whether quantum mechanics really can be the appropriate description of a large-scale complex system.